We have a problem, a math problem. And normally, math problems in astronomy are boring. They are about decimal points or error margins. But this one is different because this math problem suggests that we don't actually know what we are looking at. We have been tracking 3I/Atlas for months. We thought we knew its speed. We thought we knew its orbit. And most importantly, we thought we knew its size. But on December 23rd, a new set of calculations was published. And it didn't just refine the old numbers, it destroyed them. The new data contradicts everything we thought we knew about this object. If you believe the measurements from May, this object is a giant, a massive 5-kilometer wide mountain of ice. If you believe the measurements from this week, it is a dwarf, barely 1 kilometer wide, a fragment, a ghost. These two numbers cannot both be true. Physics doesn't allow it. An object cannot shrink by 80% and lose 99% of its mass in 6 months without exploding into a billion pieces. And yet 3I/Atlas is still there, intact. So what is going on? Are the telescopes lying? Is the math broken? Or are we dealing with an object that is playing tricks on our physics models? Today, I am going to open the hood on this paradox. I am going to walk you through the size impossible calculation. And by the end of this video, you will understand why scientists are scratching their heads. Because when the numbers don't add up, that's usually where the discovery is hiding. Let's start with the new reality, the data that just dropped. On December 23rd, scientists tried to weigh 3I/Atlas. Now, you can't put a comet on a scale. You have to be clever. You have to use Newton's second law. Force equals mass times acceleration. F equals ma. We know the object is accelerating, not just from gravity, but from the rocket effect. As the comet heats up, gas shoots off the surface. Action and reaction. The gas goes one way, the comet gets pushed the other way. This is called non-gravitational acceleration. The tracking stations measured this push precisely. The value is tiny, 89.3 times 10 to the -9 astronomical units per day squared. I know, that sounds like gibberish. So let's translate it. It means that every single day, this rocket engine is pushing the comet to go about 13 kilometers per day faster than it was the day before. It's a gentle nudge, about 1/5 millionth of Earth's gravity. But over weeks, it adds up. So we have the A in the equation, acceleration. Now we need the F, force. How hard is the engine pushing? To find that, we turn to the James Webb Space Telescope. Webb looked at the gas cloud. It measured two things. First, how much gas is leaving, about 150 kilograms every second. Second, how fast is it moving, about 1,600 kilometers per hour. Now you have the force, and you have the acceleration, so you can solve for m, the mass. You ask the math, how heavy must this rock be for this amount of gas to give it this amount of push? The answer came back clear, 260 billion kilograms. And if you assume it's made of normal comet ice, fluffy, low-density stuff that gives you a diameter of roughly 1 kilometer, maybe 800 meters. Case closed, right? We have the numbers. The physics works. It's a small, active comet. But there is a catch, a massive catch. To understand why that 1 kilometer number is a nightmare, we have to go back in time, back to May, June, July, August, September. For 5 long months, this object was being tracked by the best eyes on Earth. 230 observatories worldwide. They were pinpointing its position with an accuracy of 0.028 arc seconds. Let me put that accuracy in perspective. That is like spotting a coin from 100 kilometers away. It is sniper-level precision. For 5 months, they looked for that rocket push. They looked for that non-gravitational acceleration. And do you know what they found? Zero. Nothing. The object was coasting perfectly on gravity alone. No jets, no deviations, no drift. Now you might think maybe the push was just too small to see back then? No. The detection limit of those telescopes was incredible. If there was a push, they would have seen it. The fact that they saw nothing sets an upper limit on the acceleration. It had to be tiny, almost non-existent. And here's where the trap snaps shut. Let's go back to Newton. F equals ma. If the acceleration is 0 or extremely close to 0, but the comet is still releasing gas, then the mass must be huge. Think about it. If I push a bicycle it moves. If I push a cruise ship with the same force, it doesn't move. The lack of movement implies a massive, heavy body. Harvard scientist Avi Loeb crunched these numbers months ago. He calculated that for the acceleration to be undetectable during that period, the object couldn't be 260 billion kilograms. It had to be at least 33 trillion kilograms. That is 120 times heavier than the new calculation. And in terms of size, it means the object had to be 5 kilometers wide, not 1. So here is the contradiction. The silence of the summer tells us it's a 5-kilometer giant. The motion of the winter tells us it's a 1-kilometer dwarf. They can't both be right. So which one is lying? How do we fix a 120 times error? How do we bridge the gap between a mountain and a hill? Scientists are currently scrambling to find a theory that fits both timelines. And there are 4 possibilities. Theory number 1, the diet. Could the comet have lost the weight? It sounds plausible. Comets melt. But remember the numbers. To go from 33 trillion kilograms to 260 billion kilograms, it would have to lose 99% of its mass in 3 months. That isn't melting, that is evaporating. If it lost that much mass that quickly, it wouldn't be a comet anymore. It would be a cloud of dust. So mass loss can explain some of the difference, but not all of it. Theory number 2, the invisible push. This is my favorite. It's a matter of perspective. Remember, we measure the comet's position relative to its orbit, forward and backward. But what if the jets weren't pushing it forward? What if they were pushing it sideways or straight up, perpendicular to the orbit? If the comet was rotating in a specific way back in May, the jets could have been firing in a direction that simply didn't change its speed along the track. It was accelerating, but in a blind spot for our telescopes. Then, as it got closer to the sun, it rotated. The jets pointed back, and suddenly the acceleration became visible. It's like a plane turning on its afterburners. You only see the speed change if it flies straight. Theory number 3, the density trap. All these calculations assume 3i/Atlas is made of normal stuff. Porous ice, fluffy dust. Density, 500 kilograms per cubic meter. About half as dense as water. But this is an interstellar object. We don't know what it's made of. What if it's not fluffy? What if it's solid rock or iron? If the density is higher, the size calculation shrinks. A small, heavy ball of iron behaves differently than a large ball of cotton candy. If we are wrong about the material, we are wrong about the size. Theory number 4, the model glitch. There is a chance, a small one, that the initial zero acceleration measurement was just wrong. Maybe the sensitivity wasn't as high as they claimed. Maybe the noise in the data hid the signal. NASA has already revised the acceleration numbers down multiple times since the first paper. Science is messy. Sometimes you just have bad data. So where does that leave us? We have a ghost giant from the summer and a rocket dwarf from the winter. The truth is, likely somewhere in the messy middle. Maybe it's 2 kilometers wide. Maybe it's incredibly dense. Maybe it flies sideways to hide its tracks. But this paradox highlights something crucial. We act like we understand these objects. We assign them numbers. We give them labels. Comet, asteroid, 0.028 arcseconds. But 3i/Atlas reminds us that we are observing a stranger, an object born in a different stellar nursery, under different gravity, with different chemistry. We are trying to fit an alien puzzle piece into a solar system picture, and sometimes the edges don't fit. Right now, the models are being rewritten. New data is streaming in every night, and with every update, the object seems to change. Is it big? Is it small? Is it heavy? Is it light? The fact that we still have to ask these questions, that is what makes this story worth following. Because the most exciting phrase in science isn't eureka, it's, that's funny, that number shouldn't be there. Keep watching the numbers. Keep watching the gap, because the answer to this paradox might tell us more about interstellar space than the images ever will. In Cosmos, we trust.